Hello, students. Today, me, Curren and my friend Alex Zhou will be explaining to you guys some things about rotational energy. So please, sit back, relax, and enjoy this feature presentation. So, let's start off with the basics. Imagine that we have a mass at the end of a rod, and this rod is rotating. This mass has kinetic energy. Now, in our formal or old way of describing it, we would say that this kinetic energy is equal to 1 half mv squared. But with the knowledge that we have using rotational and rotational kinematics, we can say that V is equal to R times omega. So let's just replace V with R omega, and then we get that the K is equal to mr squared omega squared. As you can see, we group the mr squared together and the omega squared separate because in fact in rotational motion mr squared can be expressed as another quantity that we will find out in the next slide. Yep, it's I, mr squared, or the sums of all the mr squareds in a rotational solid can be expressed as I. So, we can conclude by this that K for rotational is actually equal to 1 half I omega squared. Our first example we looked at dealt with the ball at an end of a rod. Now let's deal with something else. Let's deal with a rolling ball. So obviously we can see that the ball itself is moving as well as rotating. So there's not only rotational motion, but translational motion as well. So if this is true, and the ball is not slipping, we can conclude many things about this ball. We can say that the v, or the velocity of the center of the mass, is equal to r times omega. And this will help us in a lot of different problem solving techniques and problems. So, this is the way you express the total energy of the ball. We can say that there's 1 half mv squared, which is the linear kinetic energy, and 1 half I omega squared, which is the rotational kinetic energy. And as I said, because it's rolling without slipping, we can replace omega in this problem with v over r. So we get the simplified equation shown at the bottom right of this page. Let's deal with an example problem. In this AP problem, we see a spherical object at the top of an inclined plane. This object is in the shape of a sphere, so the moment of inertia about its center will be 2/5 mr squared. We also have given mass of the sphere, radius of the sphere, height of the incline, and angle. Let's see what we can do with this problem. We will not be solving all parts of the problem because not all of them deal with rotational energy. However, we will be solving all of the parts that do deal with rotational energy. Part A of this problem asks to determine the translational kinetic energy of the sphere when it reaches the bottom of the inclined plane. To do this, we have to set our delta E to equal 0 because there are no outside external forces such as friction. So we say E initial is equal to E final. So, initially, the ball is not moving, so the only energy it has is gravitational potential energy, which is mgh. At the end, when it reaches the bottom, it has two types of energies: linear kinetic energy and rotational kinetic energy. The linear is 1/2 mv squared, and the rotational is 1/2 I omega squared. This problem wants us to find the linear, so we can say that that equals 1/2 mv squared, and we're going to now solve for that. Now we see that we solved for the kinetic energy, which is mgh minus 1/2 I omega squared. But we simplified the I omega squared by plugging in that I is equal to 2/5 mr squared for a sphere. Because it is rolling without slipping, we can say that the velocity of the ball is going to be equal to omega times r. When we plug this back in to the equation for the kinetic energy, we can get that the kinetic energy is equal to mgh minus 1/5 mv squared. We do a very similar process for part B, which asks to find the rotational kinetic energy of the sphere when it reaches the bottom of the inclined plane. What we do is we use the same equation from the first part A. mgh is equal to 1/2 mv squared plus 1/2 I omega squared. Then we recognize that the rotational energy part of this is 1/2 I omega squared. Then we move on to solve for the rotational energy, and after we do that, we get that the rotational energy will be equal to mgh minus 1/2 mv squared. Now, we have the answers to part A and part B of our problem, which involve energy. However, we have an unknown in the equation for our translational kinetic energy and rotational kinetic energy, and that's the velocity. Now we are going to use the equations that we used above to solve for the velocity. So let's just start with mgh is equal to 1/2 mv squared plus 1/2 I omega squared. Then we can move on to saying that mgh will equal 1/2 mv squared plus 1/5 mr squared omega squared. And we could say this because, again, we plugged in the 2/5 mr squared into I. Again, now we know that we are rolling without slipping. R squared omega squared just turns into v squared. So then we have mgh is equal to 1/2 mv squared plus 1/5 mv squared. Now, all we do is simplify We combine the like terms, and then we cancel out the m's, and then solve for the v. And we get that v is equal to the square root of 10gh over 7. Now, let's apply our velocity calculations to our answer from part A. We can go again and see that the kinetic energy is equal to mgh minus 1/5 mv squared. After simplifying, or not rather, plugging in the v that we just found out into the v from the answer in part A, we get that the kinetic energy is equal to mgh minus 2/7 mgh. Finally, we can simplify to see that the linear kinetic energy is equal to 5/7 mgh. Now we can do the same thing we did with part A to part B. We can plug in the velocity that we found into part B of the problem. So we get that the rotational energy is equal to mgh minus 5/7 mgh. We can simplify that to get 2/7 mgh, but there is maybe a more logical and easier way to approach problem part B of this problem. It involves energy conservation. We know that E initial is equal to E final. So again, the initial energy is equal to the final energy. So initially we have gravitational potential energy, and that will be equal to the rotational kinetic energy plus the linear kinetic energy, because that's what we have at the end of the incline. So we already know that the gravitational potential energy is mgh, and we just solved for the kinetic energy, saying it was 5/7 mgh. So we can just say that the rotational energy is equal to the gravitational potential energy minus the linear kinetic energy. And we can see that mgh minus 5/7 mgh comes again. And we can also show this way that the rotational energy is equal to 2/7 mgh. And there we have it, folks. Thank you for watching this feature presentation on rotational energy. We hope that you do well on the AP Physics exam in May. Thank you, and have a nice night.